Ionic strength of solutions and Debye-Huckel theory. So a solution is defined as a homogeneous mixture of two or more components existing in a single phase, whereas the mixing of solutions is defined by either entropy driven or enthalpy driven processes according to this equation, which is showing the relation of the Gibbs free energy with the enthalpy and entropy. So when the mixing of solution is driven by entropy, so it will being opposed by driven by enthalpy. So overall mixing must be having a negative Gibbs free energy. So here we need to consider that the mixing of solution is for liquids, but for the case of ideal gases, by definition does not have interaction between the particles. So the ideal gases does not have interaction between particles, but the ideal solution assumes there are interactions. Why? This is because without the interactions the solution would not be in liquid phase. Rather, ideal solutions are defined as having an enthalpy of mixing or entropy of solution is equal to 0. This is because the interactions between two liquids, for example A and B, is the average of the interaction between AA and BB interactions. So in an ideal solution, average AA and BB interactions are identical. So there is no difference between the average AB interactions. So average of all type of interactions is same before and after mixing. But actually the interaction between A and B are not always equal to the interaction between A and BB for the case of real solutions. For the case of ideal solution, when enthalpy of mixing or the solution is 0, it means that the negative Gibbs free energy is obtained from the negative T del S factor, which is supporting the spontaneous energy of formation depending on the enthalpy. So this process of mixing or the formation of ideal solution is known as entropy driven. And enthalpy opposed. Process for ideal mixing. But for the case of real solutions, the heat of mixing is not equal to 0, or heat of solution. So consequently, a new term is used to describe the concentration of molecules in solution, known as activity. So for the ideal case, concentration is used, but for the real case, term activity is used. So here activity A is known as the effective concentration that takes into account the deviation from ideal behavior, and it is equal to concentration for ideal mixing of solutions. So here an activity coefficient that is gamma is utilized to convert from the solutes concentration that can be either mole fraction, molality, percent by weight, etc. So here let's consider an example of sodium chloride. For this kind of electrolyte working as a solute in a solution, the activity is equal to the activity coefficient into concentration, and for the sodium ions and chloride ions we can calculate the activity of respective ionic species separately from the activity coefficients into concentrations, that is for negative ionic species. But actually experimentally we cannot calculate the activity of only cation or anion using experimental methods. The actual measured value is a combination of the activity coefficients of negative and that is equal positive species with respective molar ratios. So that's actually written in a way: the activity coefficient of the electrolyte is calculated as the combination of molar charges on the cationic and anionic species. So for the sodium chloride, we can calculate the value of activity coefficient using the simplified formula, that is equal to the, for sodium it's 1, chloride valency is 1, and 1 over 1 plus 1 is equal to Similarly, for the case of magnesium chloride, we can write the formula is equal to the sum of the activity coefficients of respective ionic species So here the activity coefficient is measured by the formula given by Debye-Huckel theory, that is given as equation number 3, in which I is ionic strength, which is actually equal to the sum of the product of molality and charge number of all ionic species present in the electrolyte solution. For example, for the case of sodium chloride, the ionic strength can be calculated as molality of sodium ions plus molality of chloride ions into -1 square. Similarly, for the calculation of ionic strength of magnesium chloride, we can write the formula as a molar solution of magnesium chloride can generate 1 magnesium ion with molality into its ionic strength of magnesium ion, that is the product of molality of magnesium into its charge square plus each molar solution of magnesium chloride can generate 2 chloride ions, so we need to multiply with 2 and the molality of chloride ions into -1 square. Now let's calculate the activity coefficient for zinc chloride. For example, if we are going to take the concentration that is equal to 0.02 molal, and we need to calculate the activity coefficient. So for this purpose, firstly we will calculate the ionic strength of zinc chloride, that is equal to the half of 0.02 into 2 square, that is the charge on the zinc ion, plus each zinc chloride is generating 2 chloride ion into molality, and charge on each chloride ion, so that should give the value of 0.6. So now we can calculate the activity coefficient, that is equal to the log of activity coefficient minus 0.509 into the product of charges on each species and square root of the ionic strength. So in this way we can calculate the activity coefficient value, that is equal to 0.56. So here the Debye-Huckel theory includes a very detailed discussion of the assumptions and their limitation, as well as mathematical development and their applications. From the value of activity coefficient, we can see that the activity of the ionic species is almost half that of the concentration. That is because of the few principal assumptions given by Debye-Huckel theory, that is the interaction known as ion interactions, as we know that when a salt is dissolved in a solvent, for example sodium chloride is dissolved in water, then the sodium ion is surrounded by water molecules, as well as the chloride ion. The sodium ions are attracted by the negative part of the water, that is the oxygen, whereas chloride ions are attracted by the positive part of the water. So on average, each ion is surrounded more closely by ions of opposite charges than by ions of identical charges. So according to Debye-Huckel theory, there is an assumption that the departure from the ideality that is shown in terms of the activity coefficient is due to electrostatic interactions between opposite ions, that is mediated by Coulomb's law, So the force of interaction between the oppositely charged ions is given by the Coulomb's law, that is given as the Coulombic force of where Z1 and Z2 are the charges on the respective ionic species that are actually charge numbers, whereas E is electrical charge, epsilon naught is the permittivity, and ER is the permittivity in solution, or also known as dielectric constant, whereas R square is the distance between two oppositely charged species. So here equation 3 gives the formula for Debye-Huckel theory, which is also used in various applications that will be explained later on. So here this equation 3 is actually derived for the real solution with application of few assumptions. So the first one is this theory is applicable only for the strong electrolytes. It means that it is assumed that the solute is completely dissociated. Second is ions are considered as spherical in shape and are not polarized by surrounding electric field. For example, for the case of sodium and chloride ions, the interaction of solvated water molecules is ignored. Only the interaction between the sodium and chloride ions is considered. Third one is solvent play no role other than providing the relative permittivity known as dielectric constant. Fourth one is ions are considered as spherically symmetric cloud of continuous charge density. So here equation 3 is actually the limiting case with application of the four assumptions as discussed before. And if we draw the plot of ionic strength versus log of activity coefficient, it's showing the decaying pattern. So this is true for the case of dilute solutions. That is less than 1 millimolar or 10 to the power minus 3 molar. So this trend line is also known as Debye-Huckel limiting law. And for the case of higher concentration, Debye-Huckel equation is given as log of activity coefficient is equal to minus a, that is a constant, where the constant A is given as electrical charge into constant P over 8 pi epsilon naught vacuum permittivity, dielectric constant, Boltzmann constant, temperature, whereas constant B is given as elementary charge square, number of ionic species, so here in equation number 4, that is actually known as Debye-Huckel equation, A naught is known as the distance of closest approach of ions. If we plot equation number 4, for the higher concentration, the experimental data will be observed to be as appearing a decaying curve. The value of the constant A and B, for example, for KBr solution in water are around about 0.51 for A and 3.29 for the case of B. So here we have most significant aspect of the result, that is prediction of mean activity coefficient as a function of ionic strength rather than the electrolyte concentration. From equation 4, we can see that for very low values of ionic strengths, the denominator of this equation is nearly equal to 1, and for this situation the mean activity coefficient is proportional to the square root of ionic strength. So here we have mean activity coefficient A is directly related to the square root of ionic strength for very low values of ionic strengths. So here we have seen that there is a quantitative relationship between the mean activity coefficient and the ionic strength that is given by Debye-Huckel theory.